Good morning, Internet. I am Matt Booyak, and in this video we'll be taking another look at the 44th problem from the Project Euler Problem Archive. Now, just to refresh your memory, this problem asks us to find pentagonal numbers p sub k and p sub j, such that their sum and difference are also pentagonal, and the value of their difference is minimized. Pentagonal numbers are given by this expression here. Now, yesterday I did a video on this same problem showing a solution that turned out to be just fast enough on modern hardware, but probably wouldn't have been adequate 20 years ago when this problem was first published. Even though it was still technically a failed approach, I thought it was interesting enough to make a video on, though you don't have to watch that video in order to understand this one. As I said, it covers a number of interesting topics, and so I would definitely recommend it if you have the time. Just to summarize the approach that we took in that video, basically we just took pairs of pentagonal numbers p sub j and d, and calculated p sub k and p sub j plus p sub k from those values, and checked to see that all four are pentagonal. Now, this algorithm turns out to be what we call an order n cubed algorithm. And there's a very technical definition behind what that means, but roughly speaking, it means that if d corresponds to p sub I, the ith pentagonal number, the size of our search space is going to be proportional to I cubed. That means even if we're only searching the first few thousand values of I, we're probably searching billions or maybe even tens of billions of possibilities. And so that's why that approach ended up being so slow. Today I'm going to show you a more efficient approach. But before we can get to writing some code, we're going to have to do some analysis. So let's get into it. As usual, we will copy our template directory to make our problem directory. We have to make a distinction that this is the fast one, since we already have a directory for the slow one. We'll go into our problem directory and open our analysis file. So when I was first trying to come up with an efficient way of solving this problem, I decided to take inspiration from the idea of a Pythagorean triple. Let's say recall if x squared plus y squared equals z squared, x, y, z is a Pythagorean triple. And there's a formula for generating these triples. If you want a Pythagorean triple, you don't have to guess and check. You can just plug in some numbers and it'll give you a Pythagorean triple. And so I wanted to find, we'll call them, pentagonal triples. And the reason why I thought this might be amenable to a similar approach is that if you look at this, expression, p sub I plus p sub j equals p sub k, if you were to expand this out, you'll recall, going back to the problem description for a moment, that this expression has this n squared term in it. And so this expression or equation, when expanded out, would have I squared plus j squared equals k squared in it, along with some other terms. And so I was hoping to find a nice formula for finding these pentagonal triples. I don't even know if such a formula exists, but if it did, not only would it make the algorithm way more efficient, it might even make it so that you could solve this problem by hand. Quite promising. However, when I started getting into the algebra and trying to actually work out what the coefficients of this formula might be, it ended up being rather tedious and lengthy, and I'm not even sure whether this formula even exists. So back to the drawing board. Let's try a different approach. When does P sub I equal P sub k minus P sub j? So rather than trying to find when two pentagonals sum to a pentagonal number, we're looking at when is a pentagonal the difference of two other pentagonal numbers. And this approach turns out to be a bit more promising. For now, I'm just going to replace this P sub I with D, because in our problem, D is the difference of P sub k and P sub j. Just be aware I'm going to use that somewhat interchangeably throughout this problem, with P sub I being equal to D. Okay, so let's actually expand this out. So let's say recall P sub n is going to be equal to n times 3n minus 1 over 2. And so we can expand our expression as, it's going to be k times 3k minus 1 over 2 minus j times 3j minus 1 over 2. And let's expand this out. So that's going to be 3k squared. Actually, let's multiply both sides of this by 2. It's going to be easier to do the algebra here if we can get that 2 out of the way. Okay, so that's going to be 3k squared minus k minus 3j squared plus j. Now, whenever I'm doing any sort of number theory type problem and I see a difference of squares, that immediately attracts my attention, because we can factor a difference of squares as k minus j times k plus j. And then that's going to leave us minus k minus j. But then you see that this term here, k minus j, is the same as this term here. And so we can factor once again to get k minus j is going to be equal to 3 times k plus j minus 1. Okay, so this is interesting because now we've written 2d as the product of two numbers. And so this kind of suggests an algorithm that we might consider for solving our problem. If we could find factor pairs of 2d with the smaller of the two numbers being equal to k minus j and the larger being equal to k plus j, maybe we can determine when those factor pairs actually lead to positive integer values of k and j. Now, you'll recall me saying that our previous approach was an order n cubed algorithm. So before we get to working this all out and implementing this, it might be a good idea to get some notion of what the running time of this algorithm would be. Well, finding the factor pairs of d is going to be proportional to the square root of d. But you'll recall that d is proportional to the square of I, assuming that d is the ith pentagonal number. And so that means that finding the number of factor pairs, or identifying the factor pairs of d, is going to be proportional to I. and then we're going to be iterating over I to generate the values of D. And so we're going to have 2 loops, each iterating over roughly the value of I. And so our algorithm is going to be an order n squared algorithm instead of an order n cubed algorithm. Much better. So now that we have some amount of confidence that this algorithm is going to be actually an improvement, let's continue with our analysis. So let's say suppose 2D is equal to A times B, with A is equal to K minus J, and B is equal to 3K plus J minus 1. All right. Now we can solve for the values of K and J in terms of A and B. So we can write K is equal to A plus J. And then we can substitute that into the expression for B over here and get B is equal to 3 times A plus J minus 1. And so that's going to be 3 times A plus 2J minus 1. Now we can solve for J. And so we'll say B plus 1 over 3 is going to be equal to A plus 2J. And so then we have J is going to be equal to B plus 1 over 3 minus A all over 2. Okay, so now given our factor pair A and B, we can calculate our values of J and K. Let's actually copy this down here. So these are our values of J and K in terms of A and B. Now we just have to make sure that they're actually valid. Obviously, you can't have a fractional or negative value of J. So the first thing we want to check is J has to be greater than 0. And we can determine when that's the case just by doing B plus 1 over 3 minus A over 2 is greater than 0. Multiplying both sides by 2 and adding A to both sides, you get B plus 1 over 3 is greater than A. And then you get B plus 1 is greater than 3A. Now, since B and A are integers, we can get rid of this plus 1 and make this greater than or equal to. So we'll say B is greater than or equal to 3A. And now recall B or AB is equal to 2D. So B is equal to 2D over A. And now we can substitute that into our inequality up here. And we come up with 2D is greater than or equal to 3A squared. And so this is going to be our first constraint. We don't want to be trying factor pairs where the smaller of the two is greater than 2D, because that will not give us an integer, or excuse me, a positive value for J. So we could say, constraint number 1. Okay? So now we want to check when is it the case that, that j is actually an integer. And the first thing is that b plus 1 over 3 is going to have to be an integer. That is, 3 must divide b plus 1 evenly. You'll note that if, in particular, we look at, excuse me, I'm looking at the wrong thing here. Let's go back up here and grab this. Okay. Yeah, so in order for this value j to be an integer, first of all, we have to have b plus 1 is divisible by 3. So let's say, when is j an integer? And so we'll say constraint number 2, 3 divides b plus 1. Okay. And the other constraint is going to be that we have to be able to do this division by 2. And so we'll say constraint number 3 is that 2 divides b plus 1 over 3 minus a. Okay. And if all of these constraints are met, then this should give us a candidate solution. That is, we will have d, p sub j, and p sub k all being pentagonal numbers, and then we can calculate p sub j plus p sub k and see that it is also pentagonal. Okay, so let's take a look at an example. So let's go back over to the problem description here. And they give this example here where 22 is the difference of 70 and 92, with all three being pentagonal numbers. So let's see if we can rediscover that pentagonal triple. Okay, so let's say d is equal to 44. And we'll say candidate factor pairs. And so we'll have 4 and 11. 4 times 11 is 44. 2 times 22 is 44. And 1 times 44 is 44. Okay, so the first check that we need to do, let me reposition the screen here just slightly, is that we need to make sure that this first constraint is met. So if we take a is 4 and we square that, multiply by 3, we get 48. That is not less than or equal to 44, and so that is not going to work. So we'll say no, that doesn't work, and that's because constraint number 1 violated. All right, so now let's try this one here, 2 and 22. And we'll try constraint number 1. So we square 2 and multiply by 3. That gives us 12. That is less than or equal to 44. So that's good. Now we'll try constraint number 2. We add 1 to 22. That does not give us a number that is divisible by 3. And so we say no. Constraint number 2 is violated. Lastly, let's check this one. 1 squared times 3 is definitely less than 44. If we add 1 to 44, we get 45, which is divisible by 3. That gives us 15. Then if we subtract 1, we get 14, which is divisible by 2. And that gives us 7. And so we get, yes, j is equal to 7. And then we add, let's see, where did that go? Did that fall off the top of the screen? Yes, k is going to be equal to a plus j, and so a is 1, j is 7, so k is going to be equal to 8. And that's exactly as we expect. If we go back over here, we see that the 7th pentagonal number is 70, and the 8th pentagonal number is 92, and 22 plus 70 does indeed equal 92. Okay, so with all that worked out, let's finally write some code. Go to our main.cpp. And there's a couple of functions I want to steal from our other solutions. So let me just open that up real quick. We're going to want this get pent. Not particularly difficult to implement, but just copy that over. And then we'll also steal this function here. I just want to give one more shout out to Jacob, who is a viewer who suggested this method for determining if a number is pentagonal. You can see all the details of that in yesterday's video. Okay, so we're going to want to iterate over the possible values of d, and so we're going to want an index I, and we'll say for I is equal to 1, no upper bound, and increment I. It's an infinite loop, so get rid of this. We're just going to exit as soon as we find our solution. And then we're going to want to find, we're going to want to calculate d first of all. So we'll say d is equal to get pent I. And then we're going to want to find the factor pairs of d. So let's say int 64 t a comma b. And we'll say for a is equal to 1. And now let's take a look at our first constraint. So going back to our notes, our first constraint here is this one here. Let's just copy this over to our code for easy reference. Okay, so we want to say while 3 times a is less than or equal to 2 times d. But actually, we're going to be using double the value of d in a number of situations. So let's actually just make that its own variable. We'll call that twice d is equal to 2 times d. Okay, so twice d. And then we're going to just increment a. All right. So first we have to check that this actually does, or a actually is the first member of a factor pair. So we'll say if twice d mod a is not equal to 0, that is, if it does not divide evenly, then we're just going to try the next possibility. If it is or if it does divide evenly, we'll say b is equal to twice d divided by a. And now we need to do our other checks. So we'll say constraint number 2. So we'll say if b plus 1 mod 3 is not equal to 0, then continue. Try the next possibility. And constraint number 3, say if b plus 1 divided by 3 minus a and 1. So this is a way that you can check if a number is odd using the bitwise AND operator. So if this number is odd, it's not going to be divisible by 2. And so then we will also continue. Okay. And so those should be our 3 checks. So now we'll say we need J and K. And we'll say J is equal to all this mess up here over 2. And going back over here, recall that K is just going to be equal to A plus J. So we'll say K is equal to A plus J. Then we'll say int 64t p sub j is going to be equal to get pent j, and int 64t p sub k is equal to get pent k. Then we'll say let their sum be p sub j plus p sub k. And we need to check that this number is pentagonal. Recall that we already know that the other 3 values are pentagonal, so this is our last check. So we'll say if is pentagonal sum. Then we'll say printf solution is equal to %LD, and that's going to be just D. Recall that our solution is going to be the difference. Out of the 4 values, that's the one that they specifically ask for. Okay, and once we found our solution, we can just return 0. Okay. Think that should all be good. Oh, one thing, I always forget the necessary include files. In order to use this is pentagonal, which uses some floating point operations, we're going to need math.h. Let's go back to our shell, and before I run our new program for you, let's at least make sure that it builds. It does, that's good. Let's go over to our slow solution for a moment. I just want you to recall just how slow our slow solution is. You'll recall well, maybe I shouldn't spoil it, but it's going to take a little while to find the solution. I'm not actually going to sit here the whole time. It won't take that long, but that just gives you an idea of how long the search takes. So let's go back over to our hopefully fast solution, and bam, done immediately. Let's try timing it. Looks like about 29 milliseconds. You may recall from yesterday's video that the slow solution takes something on the order of 30 seconds. So this is 1,000 times faster than yesterday's solution. But is it correct? Let's go back over to the archive and scroll down to problem number 44. As is always the case, the website has signed me out, So let's try signing back in. And we will scroll down again to problem 44 and see that this does in fact match our solution. So thank you so much for watching. Tomorrow there'll be a little bit of a jump in the problem numbers. I've already done problem numbers 45, 46, and 47. So tomorrow we'll be tackling problem number 48. I hope you'll join me.